Hello, welcome to our video presentation about our thesis. My name is Davine Ravael Gabriel. My student ID is 25019709992.
Hello, my name is Ferdinand Koris. My student ID is 250-199-3075.
Hello, my name is Davy from Bina Nusantara University with student ID 2501-963993.
Our thesis is about a hybrid GNN-LSTM enhancing speech emotion recognition. Now, in our video presentation, we will include all the contents about introductions, methodology, results and discussion, and conclusion in our thesis paper. Okay, so for the introduction, what is speech emotion recognition? Speech emotion recognition, or SER, is the process of inferring emotion from speech signals. It analyzes both acoustic features, such as pitch, tone, and rhythm, as well as linguistic content, the actual spoken words. However, distinguishing between the two remains a major challenge. Okay, then challenges in SER. One of the biggest challenges in SER is separating linguistic content from acoustic features. For example, the same sentence can sound neutral, happy, or angry based on how it is spoken. Traditional methods struggle to capture this distinction. So, what is the advantages in deep learning for SER, or the advancements in deep learning for SER? Fortunately, deep learning has significantly improved speech recognition. Several models have been used, including deep neural networks, Gaussian mixture models, support vector machines, convolutional neural networks combined with LSTMs. These methods have improved accuracy in SER, but there are still gaps in capturing both spatial and temporal relationships in speech signals. Why use GNN and LSTM? Now, why do we propose a combination of both? LSTMs are powerful for analyzing time series data, making them ideal for speech processing. However, LSTMs alone lack the ability to capture spatial relationships between different features in the speech signal. This is where graph neural networks, or GNNs, come in. GNNs excel at handling non-Euclidean data, meaning they can analyze relationships between data points, rather than treating them as independent elements. By modeling speech data as a graph, we can enhance emotion recognitions by incorporating both spatial and temporal dependencies. With this research paper, our thesis approach is we propose a GNN LSTM hybrid architecture for emotion recognition. We utilize it as a VEE dataset or SAVE dataset, a well-known dataset for SER research. By combining GNNs for spatial relationships and LSTMs for sequential processing, our goal is to improve the accuracy of emotion classification from speech.
Okay, now I will explain the methodology used in our research, which is designed to leverage both the temporal and relational information in speech data. First, we have dataset and preprocessing. For the datasets we use in this research are the SAVEE datasets, which have 7 different emotion classes, which consist of angry, disgust, fear, happy, neutral, sad, and surprise. Since each the speech signal vary in length, we standardize all the audio clips by padding and truncating them into 4 seconds. This will ensure the uniformity across all the audio samples. For the emotion classes distribution, we will be having 60 instances for most of the emotions and 120 instances for neutral emotions. Next, for feature extraction, in this step, we will be extracting the feature by using the OpenSmile library, which is widely used for speech emotion analysis. Our extraction process will segment the audio into 25 millisecond frames with a 10 millisecond hop size, in total generating 1582 feature values per hop. These feature values will capture the various acoustic properties, which is crucial for emotion recognitions, such as pitch, energy, and spectral characteristics. Next, we have graph construction. We will be transforming the sequential audio data into a weighted, undirected cyclic graph structure, in which each node in our graph will represent an audio frames, and the edges are formed based on two strategies. First, the backbone edges, which will connect each node to its subsequent nodes to preserve the temporal relationships. Then there is also top k similarity edges, which will link each node to its top 10 most similar nodes by using the cosine similarity distance algorithm, in which we'll capture the frame level feature relationships. Well, we choose to use a graph structure because speech signal will contain both sequential dependencies and complex relationship between frames. By structuring the audio data as a graph, we will be enabling our model to capture both local transitions and global feature interactions, and thus will improve the emotion recognition accuracy. Then for the model architecture, we will be using the GNN and LSTM hybrid approach. We choose to use LSTMs because the speech data is inherently a sequential data. In these steps, we incorporated an LSTM layer into our GNN model because LSTM are excellent at capturing long-range dependencies and contextual information over times, which overcoming the limitation of traditional RNNs and will be preventing definition gradient problem, which commonly seen in RNNs. Then for GNNs, which we will be using as our core model. In this step, our model will learn from the graph structure data for emotion recognitions, in which we'll learn from the frame representation based on their connections. The GNN models will process both the backbone edges, which contain the temporal structure, and the similarity edges, which contain the feature relationships. This will ensure the emotion-related patterns are effectively captured. The key concept of GNN models are the models will learn the node embeddings that capture both the feature data and the neighborhood structure of the graph. Finally, for the model evaluation and metrics, we will be using two key metrics, which is unweighted accuracy, which is UA, which will measure overall performance across all the emotions, and weighted accuracy, which also called by WA, which will adjust for class imbalance, ensuring fair evaluation, especially for the overrepresented emotion, such as neutral emotions, which have doubles the instances than the other emotions. Well, we choose to use accuracy as a metric because accuracy is widely used in speech emotion recognition research, in which we'll be allowing a direct benchmarking against prior work. It provides a clear measure of the model performance, and it will help assess the effectiveness of our approach in comparison of existing model.
To evaluate our results, we use 6 papers as our baseline, using different feature extraction and also models, and the accuracy ranging from 57.5% until 77.74%. And our proposed model, our proposed feature extraction, reached an accuracy of 81.7%, which is higher approximately 4% compared to the highest baseline. These results supports our hypothesis that graph neural networks effectively leveraging rich and correlated features, such as the ones generated from the OpenSmile Interspeech 2010 configurations. It is also worth noting that we don't do any excessive data augmentation, such as pitch changing or adding noise. We only use the data augmentation of truncating and also padding the audio. The longer audio will be truncated and the shorter audio will be padded, so all the audio have the same length. And we also do some similarity, or the number of k. We changed from k equals 0, k equals 5, k equals 10, k equals 15, and k equals 20. Each configuration is run 10 times and taken the highest run in order of unweighted accuracy and weighted accuracy. And the result is the highest unweighted accuracy is k equals 10, which is expected. This is our proposed solution. But something unexpected with the weighted accuracy in k equals 0. It is earned that in weighted accuracy, the highest one is in k equals 0. This raises a question. Is it really necessary to add k in our graph construction? This can happen due to the randomness of our scheduler. But due to our limitation of time, we can only use the data that we have got from each run. So the conclusion still, the best one is still k equals 10.
Okay, so the conclusion of this video presentation, is that the proposed GNN-LSTM architecture outperforms methods like PCA, LDA, and TSME. Using the SAVI dataset, audio only, the model achieves 81.7% unweighted accuracy and 77.4%. This method surpasses other baseline feature extraction methods using machine learning and deep learning without data augmentation. Thank you for listening for this video presentations.